Determine if the series is absolutely convergent, conditionally convergent, or divergent. Okay, sigma an. Let's take absolute value. Okay, this is an. Then when we take absolute value, this factor is gone because this is just negative positive negative positive. So n from 1 through infinity of negative 1 to the n minus 1 times 1 over 2n plus 3 is same as n from 1 through infinity of, this is all positive, and 1 over 2n plus 3 is always positive, so we don't have to write absolute value anymore. Okay, we get a series of positive terms. Now we want to show if this series is convergent or divergent. This series has the form 1 over 2n or just 1 over n. It's kind of, this one can be compared with 1 over 2n. The leading term on the bottom is 2n, or just say 1 over n. Let's compare this series with 1 over n. Use the limit comparison test. Okay, this is an, so just for this, an's are 1 over 2n plus 3. Okay, and take bn's, it's like leading term on the top, leading term on the bottom, 1 over 2n, or just we can just go for 1 over n. Okay, and let's take the limit of an over bn when n goes to infinity. I'm trying to use limit comparison test. That is limit n goes to infinity of an is 1 over 2n plus 3 divided by bn. Bn is 1 over n. That is limit n goes to infinity 1 over 2n plus 3. This division to multiplication, 1 over n is n over 1. Okay, let's take this limit, n on the top, 2n plus 3 on the bottom. So this infinite limit is same as the limit of leading terms, n times n on the top, 2n plus 3, just leading term 2n. So n cancel, 1/2. Okay, which is positive and finite. That means the series with terms an and the series with terms bn behave the same. Okay, we know the series with an, the sigma an, n from 1 through infinity, diverges being harmonic series, or p series with p equals 1. Since the series with terms bn diverges, this series also diverges. That means this one also diverges. Okay, this one also diverges. Since the series bn 1 over n from 1 through infinity diverges, okay, that's being a p series with p equals 1, or being harmonic series, by the limit comparison test, this series we have 1 over 2n plus 3, 1 over 2n plus 3, n from 1 through infinity also diverges. Okay, so if we take the absolute value of this series, this one diverges. Okay, that means this series does not converge absolutely, but this might converge normally because this is an alternating series. Now we want to use the alternating series test to show if this is convergent. Okay, absolutely no, it diverges, but normally let's see. So the whole thing is an, and 1 over 2n plus 3 we say bn. To use the alternating series test we say bn. Okay, we use the alternating series test, okay, on the given series, which is negative 1 n plus 1 times 1 over 2n plus 3 n from 1 through infinity. That's the given negative 1 n minus 1 or n plus 1, doesn't matter. Okay, this term is bn. Okay, let bn 1 over 2n plus 3. To use the alternating series test for convergence, okay, alternating series test is used to show the convergence. Just for the convergence, all we have to show is bn's are decreasing and they decrease to 0. Okay, first we need to show bn's are decreasing. That means the next term bn plus 1 is bn plus 1 is less than equal to bn. Okay, let's see. That is same as is 1 over bn plus 1 means replace n by n plus 1. 2n plus 1 plus 3. Is this less than equal to bn? 1 over 2n plus 3. Okay, let's simplify. Or 1 over 2n plus 2 plus 3, 2n plus 5 less than equal to, is this fraction less than equal to 1 over 2n plus 3? Okay, look, the bottom on the left is bigger than the bottom on the right. Consequently, the fraction is smaller. When the denominator is bigger, then the fraction will be smaller. So this is true. That means we just showed bn's are decreasing. Next, we need to show the limit of bn when n goes to infinity is 0. That means they should decrease to 0. When n goes to infinity, 2 times infinity, infinity, 1 over infinity is 0. Yes, that's true as well. That means the series converges. The original series converges, but when we take the absolute value, it diverges. So that means the series converges, but conditionally, not absolutely. Thus, the original series, given series, converges conditionally.